our pleasure today to welcome Rachel Cummings for the second keynote. Rachel is an assistant professor at Columbia University and doing fantastic work in the area of data privacy with connections to machine learning. And in her career so far, she has not only won an NSF Career Award, but a much larger, longer, and impressive list of awards than I can recite here right now. She will be speaking today about mean estimation under data heterogeneity. With that said, it's a true pleasure to have you here. The floor is yours, Rachel.
Thank you. I want to start by saying thank you for that kind of like fantastic intro. I'm also very happy being here. I feel like these workshops are basically time to kind of like re-meet friends, as we have all been separate. And so this is always a very like, pleasant thing, hopefully next year in person. I'll begin with my kind of usual caveat that I do have a minor speech impairment, and so if I pause briefly, don't blame Zoom. I'll be back in a second. So great. I'll be talking today about something that kind of like, as I mentioned at the end, is kind of like almost federated, and I will pose questions in the audience, not actually during the talk, like hopefully in the coming days, weeks, and months. How can we extend these things in a way that can be fully federated? And I'll say this is joint work with some like fantastic folks. All of them are at Apple, Vitaly Feldman, Audra McMillan, and like Kunal Talwar. And this is some work that like came out of my like previous like consulting work there. So the big problem that we're trying to address is sorry, can someone just like verbally say that you can hear me, because I can't actually see anyone giving a thumbs up?
Yes.
Yeah. Okay, good.
Can hear you.
Okay, good. I have this like, terrible fear. I will talk in silence for like 20 minutes and then everyone will be sad, including me. Good. So yes. So we're thinking about like, how can we do tasks like, federated learning of kind of word like prediction of like text emoji use. And we're going to be thinking particularly of very like, heterogeneous users. And in particular, different users may have like very different texting patterns. They may have different word use, and we'll call that user-specific distributions. And we also know that like different users may have different levels of like texting use, meaning they may type different kind of like numbers of words every day. And so if we're taking a sample, this means we're going to have varying quantities of the kind of like per user data. And of course, because I am me, we're going to be thinking about like privacy questions in this space. And this example is one where, of course, texting content is going to be highly sensitive, but you can think about kind of like, many more applications where a device is going to be collecting data, and we may want privacy of that. So we are kind of unfortunately not going to solve that problem today. We're going to kind of like abstract things away into a somewhat simpler framework. Our goal today is going to be simply, how do we estimate the mean of a distribution under these cases where we're going to have kind of like a heterogeneous user data distributions and also user quantities of data. So we're going to think of a global distribution D that we would like to learn. And let's say it's going to be between 0 to 1. And there's some mean P and some variance sigma squared P. And our goal is to kind of estimate P. How do we do this based on data? We're going to have a bunch of users, and they're each going to sample their own personal distributional parameter from the underlying global distribution. And so this is where kind of like heterogeneity comes in, is they're going to have different parameters. And they're also going to have different quantities samples, and we'll say that kind of like Ki is a quantity of samples held by the ith user. And so these two parameters, Pi, Ki, are going to be used to like generate user data. And so we're going to say each kind of user I is going to like generate Bernoulli data with a parameter Pi, and they're going to have Ki samples. And our goal in this work is going to be use these samples, Xij, taken from kind of all of the users, to learn the mean of the underlying distribution privately. So let's start with a kind of like simple warm-up in the case where we don't care about privacy yet, and we just want to kind of do this like estimation. Every individual is going to have like their own personal estimate of the mean p, and we'll call this pi hat. And this is just a kind of like empirical mean of their points. And the analyst can combine these points in a way that should provide like a higher weight on the individuals who have more data, because that means these estimates pi hat are going to be a more accurate estimate of the thing that we're actually trying to learn p. And so one approach is to just take a kind of linear combination of these points where the weight is going to be inversely proportional to the variance of this kind of individual estimator. And like in this case, in a perfect world, this is going to be a kind of unbiased estimator as long as the weights sum to 1. And this is going to have optimal variance. So like, great, we're happy it's done. One problem in this space is that we want to kind of like weight the contributions of the users inversely proportional to their variance, but we don't know the variance of the data because this depends on some like underlying parameters that we don't know, and in particular, the kind of mean and the variance of D. And so we have unfortunately reached like circularity because we're saying if we know P, then we can estimate P. So not particularly helpful. Although the nice thing is we do only have estimates of the mean and the variance, and then we can like plug these in, push these forward to like compute the optimal weights and therefore the optimal estimator. And so we're going to think about moving from this kind of like ideal case where we can just compute anything into something realizable that we can actually compute based on the data. And so we can, for example, compute some kind of like initial naive estimates, even if they aren't optimal, as long as we have sufficiently accurate estimates of the mean and the variance, we can then use that to kind of estimate individual variance and then use that in the optimal weights. So like, there's a few steps here, but it's not so hard. Now let's try adding privacy. And I'm going to assume, because of the last hour, I don't have to go into like a particular detail about like differential privacy. So I'm not going to go through these slides in like a particular detail. If you're unhappy, scream, and I'll talk more about DP. But of course, our goal here is to just think about how can we do this process under the constraint of kind of epsilon delta differential privacy. And again, the goal is to learn about the population without learning about the individual. And this is like especially prescient here because we know that if we kind of rely solely on these individual estimates, we're going to have a biased estimator because the kind of like realizations of a single PI is going to be biased with respect to P, even though they may be like unbiased in expectation. And we're going to use the kind of Laplace mechanism. Again, I'm not going to fully present this slide because I assume everyone here knows it. We're going to think about sensitivity of the function that we are like computing here is being the kind of maximum change in the function value caused by kind of one person or by one person's data. And the Laplace mechanism is going to first like compute the true answer, and will then add Laplace noise that will scale with this sensitivity over the epsilon of our like a desired privacy parameter. And the Laplace distribution looks like this. Higher variance corresponds to kind of like larger values here. And so now like for this audience, the only thing I really want to kind of emphasize on my kind of like a boilerplate privacy slides is that we're thinking about talking about user level privacy. And this is important because if we talked about event level privacy, everything would be easy. I could just invoke the like Laplace mechanism, and because like every data point is going to be bounded between 0, 1, they were kind of done. We're thinking about user level privacy here, which means I want to protect all of the KI points corresponding to kind of one person's data. And so this is, of course, a little bit harder because we have to hide a kind of like larger change in the data. And this is going to be our goal today. And again, achieving user level privacy is going to be harder when you have like a different users providing different quantities of data, because you can't simply like upper bound how much impact one person's contribution may have, because there may be tremendous like disparities in the data quantities. So back to our private solution. One kind of thing that we can do to make the non-private estimator private is we can simply apply the like Laplace mechanism. And so we're going to still take these same weighted average of our like individual estimates, where the weights are going to be inversely proportional to the variance. And we're now going to add Laplace noise that will scale with the max weight over epsilon, because in fact, this is the kind of like largest contribution any kind of like one person's data may have, is it may be the weight times the like pi hat, and this is going to be between 0 and 1. And so therefore, this is the kind of maximum contribution any one person can have. One problem in this space, and the reason why this isn't a kind of like, immediate answer, is that like at the max weight might be too large. And in particular, think of a case where kind of like one user I has kind of a very, very large number of samples or points, and kind of everyone else has one. Well, so then like this weight is going to be close to 1 for that person, and we're trying to estimate something that kind of lives between 0 and 1. And so in this case, having just this like sensitivity is going to be too large, and we cannot guarantee that we'll have like an accurate output. What we can do instead is we're gonna use like kind of like two key tools in this work to be able to reduce sensitivity and therefore noise. And the first one is we're going to like truncate pi hats to kind of like live in some range, AI, BI, and this should be strictly smaller than the range 0, 1. And so then we can further reduce sensitivity. And the question is like, how do we choose these things? Like we can't just like, arbitrarily truncate it, because we don't know the mean. And so some things may be lost in this process. We do know a few things. So we know that like, assuming D is kind of like reasonably well like behaved, we know that our pi hat is just like an estimate of P. And so it should be close to P with high probability up to some like concentration terms. And so you can choose these bounds to be just P plus or minus concentration terms. And so we go into more like specifics of this in the paper, but I will say say that kind of like for now, at least like on this slide, we're still thinking about this kind of like ideal case where we haven't necessarily made this kind of like realizable yet. That'll come soon. And so it's fine for now that we think of the mean plus or minus terms. Of course, we're going to address that in a couple slides. And so kind of like these terms should like depend on the ki of the user, how many points do they have, as well as on the variance of the underlying distribution. And so then we can take these points and then we can kind of like truncate pi hat to kind of like be in this range, ai, bi, meaning that if it's like outside of this range, we'll just like project it in. And so kind of like, as long as we choose these terms appropriately, we're basically saying pi hat should be no further than kind of like this range with high probability. And so that also says that kind of like with high probability, then like a truncation is not going to affect how we're like personalized estimates. And so effectively in this process, we're going to reduce the variance of the noise in a large way at a potential very small cost in the bias, and the small cost will depend on these like probability bounds. And of course, there's more like specifics in the paper. So then we have this, and so we are kind of moving closer and closer towards a thing that might have kind of like nice accuracy. And so here, in fact, like the main change is that we have like truncated these kind of individual estimators, and then we're allowed to like to kind of like shrink our noise parameter as well. And because these things should be kind of like strictly between 0 and 1, this term will be also less than 1, and so we're getting better. One more key idea that we have is to like truncate the weights. And so it might be the case these weights are too large. In particular, if you have too large of a disparity in the KIs, and this means the person that has many samples should get like a very large weight and kind of everyone else should be very, very small. We don't want that in terms of privacy. And so then we can like truncate the weights using some bound t. And I will say, I think this like particular expression is not particularly intuitive. You might want to have some bound t here in the max weight. But unfortunately, because you have to kind of like normalize things, you can't quite have t be both correct and also like intuitive. And so of course we opt for like correctness, but for kind of like intuition, you can think of some bound t here. And so effectively this like parameter t is going to balance a trade-off in the estimator here, which is going to be kind of minimized by assigning higher weights to those who have more data, and like the variance of the noise that is going to be minimized by kind of assigning everyone equal weights. And you can just solve this like optimization problem and kind of like find the optimal t. This again will like depend on your like distributional parameters. So now let's try to make this realizable. And like unfortunately, we are very sad that we now have to privately estimate a bunch of new stuff. And so it's not just like the variance of these like individual estimates, but it's also these like truncation parameters of the kind of estimates and the weights. Fortunately, all of these estimators only rely on the mean and the variance of the kind of underlying distribution. And I show in the paper how this is true. And so we're going to take the same approach here in the private case, is we're going to use kind of initial, possibly suboptimal private estimates of the mean and the variance to compute all of these things, and then, these to then compute these things, and then you can compute the optimal weights and the final estimator. And as an example of these, you can, for example, privately compute the mean using just a single sample from a constant fraction of the users and then applying Laplace mechanism. For the variance, we have Karwa-Wadhan gives a tool for privately estimating variance of a Gaussian, and so we have a kind of slight extension into a more general D, but it's basically that tool. And I want to emphasize here that we're not saying this is kind of a single algorithm and you must use these, but rather we're saying this is a framework, and if you have your favorite initial private estimator of the mean and the variance, perhaps they can be locally private, perhaps this can incorporate federated learning. Any other private accurate estimator can be plugged into this process. And so here now, the main result is that this process is both private and is optimal. And so of course, doing this, as long as you have private initial estimators, everything else is going to be private by just a composition and post-processing. And in terms of optimality, we use a Kramer-Rao style proof to show that under some mild assumptions on D, basically that it's a sufficiently well-behaved and can be learned based on samples, and assuming that your kind of initial estimates that you plug into this framework are going to be sufficiently accurate, then our private estimator is going to be min-max optimal among the class of a differential private, nearly unbiased estimators up to some log factors. And there is unfortunately not a version of this available yet. This work is going to appear at a primal in a few weeks, 3, 4, 5. We do plan to have a public version of this before then. And so I want to close by kind of talking about how does this relate to actual federated learning, because I began with this important federated problem, learning a language model based on kind of heterogeneous sensitive user data. And then I solved a nice problem about kind of computing means. And so I want to talk a little bit about that. So in fact, our approach is kind of almost federated. What does it mean? So it is based on these kind of individual estimates, pi hat, and those can be computed on device and then shared. However, interaction in between with these kind of initial estimates, compute this, return it, compute something else, it requires non-trivial coordination. And so it's yes, this can be done in a federated sense, but it's really it feels unfair to kind of claim this is federated. And so this means we get to be in the fantastic position of kind of posing a bunch of new open problems. I don't know if they're new. The kind I personally would always rather write the first paper than kind of the last one on a topic. And so this is fun for me because there is very natural extensions to this possible in terms of how do we move this into the kind of a completely federated version. In a bigger picture, I think there's also a lot of extensions of this work. Some of them are kind of immediate, like the first two, and then I end with a grand challenge. And so the first two is thinking about a personalization. Everyone knows their own personalized testament, and they receive a kind of a private a population level estimate. Perhaps they can do some kind of like a JDP approach to kind of like incorporate all this information and provide like a more accurate estimate of their own parameter. Additionally, kind of like extending this into the problem that I began with, language models. These are really just like, histogram questions of kind of like frequency of words. And so you can imagine running this algorithm on kind of each bucket where you just have like, Bernoulli data, binomial data, how a word either appeared or not. And I think perhaps like, a larger question that we particularly in this community have to think about is kind of like user level privacy when you have either like, heterogeneous contributions from each user, or perhaps like, a very large number, like perhaps in a streaming setting where we're doing like a continual analysis. And of course we have like, composition theorems and also group privacy. But I think the most interesting research question is when kind of the like, per user contributions are too large to really just like apply like a group privacy. So I will end there, and I'm happy to like have any questions if we have time.
Thank you, Rachel, for this wonderful talk. And please feel free to post questions in the chat or just chime in with questions here as well. Perhaps let me kick it off. And this talk is actually very much on point because we're looking at these questions also both from the federated learning perspective, but also from a pure analytics perspective, where there's interest in computing statistics over decentralized data across devices, and a mean is certainly an important statistic that comes up in many use cases. Do you have a sense of how close existing techniques for mean estimation with some user bound or some user contribution bound come to your lower bound that you derived here?
Yeah, so I don't have a real answer to that. I mean, I think in part there's simply being kind of like not enough work on this question. And I won't say none, because there certainly has been some work, but I think this is a problem space where kind of in general, we can do much more in kind of understanding it. I feel like if I were to draw kind of like a metaphor, I think we have like, a handful of papers understanding here and here and here. We don't really have a full picture of the landscape. And in fact, we like, began this work thinking like, oh, here is like a cute, like a toy problem that we can think about in the like, simplest case imaginable before we try to kind of extend into these more like practical problems. And we were kind of shocked that this problem like hasn't been solved yet. And I think this problem in general, and my final grand challenge, is one that certainly large organizations, including Google, have to grapple with, which is a kind of, you guys are getting a very, very large number of samples from each user. And kind of all of our like group privacy guarantees are fine if you get like 4 samples or like 20 samples, but it doesn't really work if you're talking about like, 100,000 samples from each user. And so I think this question of kind of like, how can we handle large number of like contributions from each user is important. And kind of like one thing that you can do that in fact maybe kind of like federated learning is our friend here, is we can have each user compute kind of like one single statistic based on their data, send it. And then it actually like it doesn't matter how many samples were used in that process, because they're kind of only sending one thing or 2 things or 5 things, but like, a small number. And so this work we realized like, heterogeneity and the number of samples became very important because kind of like the optimal thing from a simple analytics perspective is really at odds with kind of what we need to do from a privacy perspective, which is like, treating everyone's individual sample the same.
Thank you.
Yeah.
I see a question from Monica. She asks, thanks for the amazing talk, really interesting. Can you expand or point to some references for the range estimation part of the algorithm?
Yeah, sure. And I see we also have a question, Zhang Shu. Unfortunately, there's no public version of the paper yet, but hopefully in 3 to 4 weeks is our goal. So like hopefully very soon. But yes, so basically, back to the question of this kind of like AI BI, is you can think of this in the same way if you were to like have points sampled from a Gaussian. It's like you can say, imagine that I have like, 10 points sampled IID, a Gaussian that has mean 5 and variance 2. I can then compute using this kind of like a concentration inequalities. If I want to say that with kind of like probability, like at least one like minus beta, I want to be no more than some alpha distance away from the mean. And so we're basically doing that. Things are slightly more complicated because we are trying to keep D as like general as possible without assuming it's a Gaussian or it's uniform or it's blah. And so we have to write the expression for these terms in kind of like a weird way that is like a general function of the mean, the variance, the high probability guarantee, and the number of samples held by each user. But I think really intuitively, if you don't look too closely at the math, we're basically just doing like, concentration inequalities. If you know how many samples you have in the variance, then you can just like write down these expressions.
Thank you.
Yeah.
Yes, thank you again, Rachel, for this insightful talk. Wonderful to have you with us today.
Sure, thank you. Absolute pleasure.